Hi everyone, this is Dr. Perpich. I'm going to be going over for you an example of how to do the antibiotic resistance homework. And so the first thing you want to do is to pick a target for your antibiotic. Now generally what you want to do is pick something that's essential for the bacterium and it's only found in the bacteria. So the one I've picked is called the CLP-P protease. Now proteases are enzymes that degrade other proteins, and bacteria control the activity of this protease tightly because they don't want to degrade essential proteins. So if this enzyme were just active all the time, it would degrade essential proteins and the bacteria wouldn't be viable. And it turns out if you knock this out, in some bacteria they don't grow at all. And one example is Mycobacterium tuberculosis. So let's go through how this actually works. Ordinarily there's an ATPase that controls the activity of the CLP-P protease, which I'm showing here, and normally it's inactive. But under the right conditions, the ATPase can become active. And I'm just going to show the CLP protease active with sort of a larger hole in the middle, because now it's able to accept certain proteins, which I'm just going to call selected proteins. And it can bind these when it becomes activated and degrade them into amino acids. So this system is non-essential in some bacteria, but knocking this out can cause the bacteria to become more susceptible to antibiotics. It can also cause them to lose their virulence. So we could design an inhibitor that would just block this enzyme, but it might be more interesting to design an activator, because if you think about it, if we can cause this to degrade essential proteins and just stimulate its activity, that might be an effective antibiotic. And so if we design a stimulator of this, draw this again, so normally it's inactive, but now if we make an antibiotic, I'm just going to call it antibiotics, ABX, perhaps kicking out the ATPase so that it can't keep this enzyme inactive. Now here we have our CLP protease that's active all the time. So the drug has come in, it's bound the ATPase and kicked it off, and now the CLP-P protease is just active all the time. And if that's the case, now what you can imagine happening is that you have all these different essential proteins, and they can then be degraded. So if we use our antibiotic and stimulate the activity of this protease so that it's active all the time, we degrade these essential intracellular proteins and the bacteria are no longer viable. Now it's good to give your antibiotic a name, so I'm just going to call this one CLP-STIM, since I chose to design an antibiotic that actually stimulated instead of inhibited this bacterial protein. So it turns out that the CLP protease is present in many bacteria, so this could actually be something that would be a broad spectrum antibiotic. So if it's present in all bacteria and it's essential, then you would expect its spectrum to be broad. So what are some ways that these bacteria could become resistant? Well, one potential way would be if the bacteria made a mutation in the CLP-P protease such that it no longer was active and wouldn't degrade essential proteins anymore. So one potential advantage of making an antibiotic that stimulates activity of the protease is that if the bacterium inactivates it, as I told you before, inactivating this actually causes the bacteria to become more susceptible to other antibiotics, and it decreases their virulence. So this might actually be a good thing for us if the bacteria made a mutation that inactivated the protease altogether. Now, there are other mechanisms by which bacteria can become resistant, and those can be many things, but one could be like drug efflux. So instead of mutating the target, the bacteria can actually pump the drug out of the cell and become resistant that way. One other consideration are, what are the side effects on the host? Because it turns out, of course, that that people and animals have proteases, and these are involved in things like blood pressure regulation. They're also involved in coagulation and also glucose regulation. So if we made a drug that also inhibited or interfered with these processes in humans, that would be very bad. Obviously, we don't want to have our patients have blood pressure regulation problems, certainly not coagulation problems or glucose regulation problems. And so we always try to design a drug or a compound that's going to be specific for the bacterial version of the protease. And for this particular target, the CLPP protease, that might not be too difficult, but for other targets it might be. So you can base your antibiotic on something that's real, kind of like I did here, or you can make something up, as long as you have a clear mechanism and you're thinking about trying to find targets within the bacteria that are specific to the bacteria and minimizing side effects. So use your imagination, have a little bit of fun with it, and if you have any questions or are having problems with it, please feel free to contact either myself or Dr. Yoder Himes, and we'd be happy to try to help you. So I hope that this was helpful to you, and best of luck.